I haven't received a reply from them, so I'm not sure if the same problem will happen today. So I changed the content of today's lecture. So previously I planned to introduce recommendation systems, but then because I'm not sure about if the system works today, so I decided to give some introductions to these projects: HDFS, NoSQL systems, and HBase as one example of the NoSQL database, and finally it's about the Hive project. So today's lecture will be very easy to understand, but there's no algorithms and there's no difficult concepts to understand. So you could just relax, and also the most important part is that today's lecture will not be in the exam. So so that's why if some problems happens in today's lecture recording, then it's not a big problem, okay? So for you guys who might be interested in these projects, so you can listen and also try to practice in next week's lab. So next week's lab, I'll give you some instructions on how to HBase and Hive to do the big data problems. And talking about the fourth project, I think also because of the problems of lecture recording, so the web stream students, they could not understand the many details of the project. So I decide to give you 1 more week for this project, which means the deadline will be in the beginning of June. So I hope that you could utilize these 3 to 4 weeks to do a good job, because the first project is not that easy, and especially the efficiency is very important. So as I introduced, you can use very naive algorithm to solve this problem, but you are not able to do this in a short time period, especially on AWS. Maybe you will take hours if you just use a very naive algorithm. So the one good algorithm should be able to finish within 10 minutes for the project for the dataset given to you, okay? And I think excellent algorithm should finish within 5 minutes on the largest cluster. So there's a lot of room for improvement. You can try to improve algorithm. And the paper provided to you is one possible solution, but it's still not the best one. You can see that the paper is published about 8 years ago. So recently there are also some papers on set simulator join. And if you are interested, you can try to read the recent papers to see if you can get some idea from them and to accelerate your existing algorithm. So, but also be careful of the budget, so you have $100 credits. And so test everything locally and then move to AWS. And also follow the lab instructions. So this week's lab is about how to use Spark on AWS. So first finish this week's lab and then begin to do this project on AWS, okay? And if you have any problems on the AWS credits, you can contact me and I'll try to find a solution for you to get more credits, okay? So now let's start this lecture, and it's about HDFS, NoSQL systems, HBase, and Hive. And so we have learned MapReduce before, and MapReduce and Spark, they both use HDFS as a storage. So today we'll see what HDFS is like and why it can be used for big data storage. So file system, as we all know, is just like a tree structure, right? So like in Unix-like style operating systems or Linux. And so the root directory, under the root directory, we can create several folders or directories. And all the files will be stored in the leaf node of this tree structure. So this is what a file system is like on a single machine. File system is a master data structures that an operating system can use to keep track of the files on disk or partition. So it means that the file system will help you to organize the files and directories on the disk. And in many traditional cluster architectures, so the storage is viewed as a distinct and separate component from the computation. For example, so these are the the nodes for computation, but data is not stored in these nodes. It's installed in some other places, such as NAS or ICN. For these are where the data is stored. And if you do some tasks, you need to move the data from the storage to the computation. So that's a traditional way. But the problem here is that if the data size is very large and the link between the compute nodes and storage nodes becomes a bottleneck because you need to transfer a lot of data between the storage nodes and the compute nodes. And so that's a problem of traditional cluster-based computation. And besides, based on the distributed environment, and the file system a little bit different, which is called a distributed file system. And the idea is that, so we don't move data to the workers because this is not very efficient, right? So we need to do some data communication between many computer nodes. But instead, we can move workers to the data. So where the data is and where the computation will happen. So that's a basic idea. So we store the data on the local disks of nodes in a cluster. And then, so based on the data one node has, and we start up the workers on that node to do some computation using the data the node has. And well, so actually you can see that that's how MapReduce deal with the big data problem, right? So the data is stored in the cluster, and then the map tasks and reduce tasks, the map tasks is moved to the data. And also the number of map tasks is also determined by the number of data chunks or data blocks in the cluster you used. And the reason is that, okay, so it is not, on a single cluster, it's not enough, we do not have enough RAM to hold all the data in the memory, right? So, and also disk access is very slow. And but the disk throughput is reasonable. And about the low latency and throughput, these two concepts I will introduce in the next slides. So because of this, so that's why we can utilize this idea to do the distributed computation. So we don't move the data to the worker, we move the worker to the data. And so, as a result, so distributed file system is designed based on this idea. So a distributed file system is kind of a client-server-based application that allows clients to access and process data stored on the server as if it were on their own computer. And in Google published their paper about GFS, a Google file system, more than 10 years ago. And then following the idea of GFS, so a Hadoop project developed the HDFS project, Hadoop distributed file system, for Hadoop MapReduce. And so that's what we have used in this semester, right? So remember that in the labs, you always use HDFS, DFS, put, get. All these are based on the HDFS APIs. So you store your data in HDFS, and then you also do the computation based on the storage provided by HDFS. And okay, so what is latency and throughput? So latency is the time required to perform some action or to produce some result. It is measured in units of time, like hours, minutes, seconds, milliseconds, nanoseconds, or clock periods. So just to measure how much time you need to spend on some operation. So for example, I/O latency, which means that the time that you need to you take to complete a single I/O read or write. So that's called I/O latency. And throughput is a different concept. It is a number of such actions executed or results produced per unit of time. So it is measured usually in units of whatever is being produced, such as data, per unit of the time. So for example, the disk throughput is a maximum rate of sequential data transfer measured by megabytes per second or gigabytes per second, something like this. So that's throughput and latency. So for disk access has low latency because for one I/O read or write based on disk, and you need to spend longer time compared to the memory operations. So if the data is in memory, if you fetch data in memory, is much faster than fetching the data from disk, right? So it has a low latency, but the throughput is okay. So if you read some data from disk, every second actually you can read many data. So maybe several megabytes per second. This measure for the disk throughput. And the assumptions and goals of HDFS is like this. So it assumes for big data problems, okay? And for big data problems, it assumes very large data sets, not like what we do every day in our own computer or in our laptop. So it is not designed for small files, for many small files. It's designed for not many, but very large files. And also the reading and writing behavior is kind of streaming access. So designed for batch processing, not for random access, not for interactive use by users. Okay, so normally it is, you can read the file from the beginning to the end as kind of a sequential read, or write the data to disk from the beginning to the end. But normally it's not like you read some data in between or update some data in the file. So in that kind of problems, HDFS is not good choice. And the emphasis is on high throughput of data access rather than the low latency of data access. So now you can see, based on the two concepts, you can try to understand about the goal of HDFS. It aims to provide high throughput, which means that every time unit, well, your application is able to read or write a lot of data from disk or to the disk. And it's not for low latency of data access, which means that it's not for good, fast reading or writing of the data. So that's two different ideas. And about coherence model, it's utilize a simple model. It's built around the idea that the most efficient data processing pattern is write once and read many times pattern. So it assumes that your data can be read for many times, but mostly it's a sequential read. But normally it can be written just once or just a few times and will not be updated. So this kind of data analytics problems, right? So the data set is already given to you. So what you need to do is just put data to the file systems, and then you don't need to write something to this file again. You just need to do some analytic jobs based on the data you already have. And a file, once it's created, written, and closed, need not to be changed except for append and truncate. So you can append some more contents to the existing file, and you can also truncate the file to different parts. But normally we will not do some kind of update which requires random access in the file. And moving computation is cheaper than moving data, right? So this is what we have seen before. So the HDFS also utilize this idea. And the data locations exposed so that computations know where we can move to based on the data a node has. So based on this computer, so what kind of computation can be performed depends on what kind of data this computer, this node has. And it also assumes commodity hardware, which means that the hardware used in the cluster will not be very expensive. It's kind of cheap hardwares. So the files are replicated to handle the hardware failure. And because there are many disks in the whole cluster, right? So almost at any time, there may be some failure in your cluster. So HDFS just use replication to deal with fault tolerance. And hardware failure is normal rather than exception. So it assumes this is a normal behavior. It's not exceptional behavior. So detect failures and recover from them is very important as a goal in HDFS. And the portability across heterogeneous hardware and software platforms is also very important in HDFS. It is designed to be easily portable from one platform to another. So you can use HDFS in different platforms, in different operating systems. And it is not suited for low latency data access. HBase, so we will learn later, is a better option. So HBase can provide better latency for some kind of real-time jobs. And it's also not suited for lots of small files. And this is because the cost of managing these the metadata for these small files is very high. So we will see some details later about HDFS. So there's a component called name node. Name node is used to hold the metadata in memory. So normally you only have 4 gigabytes memory to hold the metadata for your file organization. So if you have many small files, which means that this 4 gigabyte memory may not be enough to hold all the metadata. So it will cause some problems in HDFS. So in summary, HDFS is a distributed file system provided by the Hadoop project and designed to run on commodity hardware, not on expensive hardwares. The basic features include it is suitable for applications with large datasets and not for small files. And it assumes streaming access to file system data, sequential read and sequential write. And normally it's write once and read many times pattern. It aims to provide high throughput, but not for low latency jobs. It can be built out of commodity hardware. So as a result, the failure is normal instead of exceptions. So the highly fault tolerance must be guaranteed in HDFS. And the architecture is like this. So HDFS is a block structured file system. So the files are split into blocks. And the size of the block can be configured in HDFS. Normally it is about 64 megabytes or 128 megabytes. And a file can be made of several blocks, and they are stored across a cluster of one or more machines with data storage capacity. So this is one example. So assume you have one file, and this file has 5 blocks. So each block will be replicated for some times. In this example, it's replicated for 3 times. And the different blocks will be stored in different locations to guarantee the availability of all the data blocks. So if on one node, some data is lost or missing, such as here, the number 2 block is missing or corrupted. And then HDFS knows that, okay, I have another 2 copies for this data. So I also know their locations. So I will go to that locations to fetch the copy and then create a new copy for this data to guarantee the availability. So that's the basic idea. It uses master-slave architecture. There are 2 types, and actually it's 2 types and 1/2 of machines in a HDFS cluster. One is name node, one is the data node, and another one is called secondary name node. So you can think about when in your first few labs, you were told about to use GPS, this comment, to check the status of whether HDFS is already started, right? So if you can see the process of name node, data node, secondary node, which means that your HDFS is already started successfully. And so name node, so it is the heart of an HDFS system, a file system. It is used to utilize it maintains and manages the file system metadata. So what is the metadata? For example, the name of file and the time the file when the file is created, and the size of the file, something like this. So it's just the attributes of this file. These are called the metadata. And also includes what blocks make up a file. So the block positions, for a file, and on which data nodes those blocks are stored. There's only one name node in an HDFS cluster. So in your cluster, only one node is used as a name node. And data node is, according to the name, it's used to store the actual data. It serves read, write requests and performs block creation, deletion, and replication based on the instruction from the name node. So it receives the instruction from name node and does the corresponding operations. And in the cluster, there are a number of data nodes, and usually one data node on one node in the cluster. And each file is split into several blocks, and these blocks are stored in the data nodes. And secondary name node, so according to the name, it seems to be a backup of the name node, but actually it is not a backup. It's kind of a checkpoint node. So it periodically merge of the transaction log from the name node. And the idea is to help the name node start up faster next time. So the details will be explained in next few slides. So let's look at the architecture of HDFS. You have one name node in the cluster for the HDFS system, and you have many data nodes to hold the actual data. And you also have one secondary name node, which is utilized to do the checkpoints management for the name node. And within name node, you organize the metadata for all the files. And there's also a FS image to record all the operations for the files in the HDFS. For HDFS client, so actually your MapReduce program is kind of one HDFS client, because it needs to ask for data from HDFS, right? So your client, your program will contact the name node and to ask for data. And the name node will tell the client where the data is. So then the data node, the corresponding data node will send the data to the client for the further operations. And for between the name node and data nodes, and there's some other operations such as replication, balancing, and heartbeats. So the name node will send the heartbeat to each data node to check if the data node is still alive or there's some problem. And the data node is stored in your local disks on each node in your cluster. So that's the whole architecture of HDFS. And what is a name node? It is used to manage the file system namespace. Okay, so it maintains the namespace tree operations like opening, closing, and renaming files and directories, and also determines the mapping of file blocks to data nodes. So it utilizes to record. It will record where the data blocks are in the data nodes. So actually, your client will always first contact the name node to get locations, and then to fetch data from the corresponding data nodes, and also store the file metadata, some attributes of the files, and also coordinate the file operations. It will direct clients to the data nodes for read and write, because the location of the blocks are stored in the name node. So it will tell the clients where to get data from which data node. And no data is moved through the name node, so because name node does not store any data, it only stores the metadata for the files. And it also maintains overall health, because there are many computers, right? So you need to check the status of each node. So who will do this? The name node will do this job. It will collect block reports and heartbeats from the data nodes. So the block reports are generated by the data nodes. The data nodes will report so which block is available or which block has some problem, and this will be received by the data nodes. And the heartbeats is sent from the name node to the data nodes to check if the data node is alive. And also there will be some kind of block replication and rebalancing, because data may be deleted, right? Some data may be deleted, and after some data is deleted, and the storage is not balanced across the whole cluster. Remember that computation is moved to the workers, right? So if your storage is not balanced which means that your computation is also not balanced. So in order to guarantee the work balance, load balance, then you must need to do the rebalancing. And the re-replication is to fix the broken blocks, because some blocks may be lost. Then you need to do some replication to guarantee that each block always has 3 copies, and also for garbage collection. And HDFS will keep the entire namespace in the memory. So it's easy to understand, because it's much faster to access the memory to get data compared to access the disk, right? So we normally 4 gigabytes is allocated to the name node for keeping the entire namespace. And so as introduced before, if it is not there, if there's not too many files, so 4 gigabytes is already sufficient for the management. But if there are too many files, huge number of small files, then this may cause some problems in this part. And the metadata of files include a list of files and list of blocks for each file, and a list of data nodes for each block, and some other file attributes. And a transaction log, which is also called edit log, is used to record the file creations and file deletions. So all the file operations will be recorded in this edit log. And the data node is responsible for serving the read and write requests from the file system's clients, such as MapReduce. And it will perform the block creation, deletion, replication upon instruction for the name node. And so now here is about block report. So each data node will send some block reports periodically to the name node to tell the name node about the status of the existing blocks on my node. And it also facilitates a pipelining of data to forward data to other specified data nodes. Okay, so the name node and data node will need to do some communications. What we have seen now is called heartbeat block reports. So block reports is to from the data node to the name node, which report the block's status. And heartbeats is sent from the name node. The heartbeat is sent from data node to the name node to confirm that, okay, to tell name node I'm still alive, I still have heartbeat. And normally it's about once every second, then 1 heartbeat will be sent from the data node. And name node will mark data nodes without the recent heartbeats as dead, and does not forward any new I/O requests to them, and also do some kind of replication. Because if one node, data node, does not send heartbeat back to the name node, there may be something wrong in that node, a network failure or disk failure or some other failure on that node. And the name node will receive the heartbeat and block reports from each data node in the cluster periodically. So this is this figure shows that how the communication is between the name node and data node. And so the heartbeat is based on the TCP protocol. So this is a name node, and every 3 seconds, the data node will send a heartbeat to say that, hi, name node, I'm alive. So the name node will record this message to, okay, so you are still alive. I will send a further read or write request to you. But if for some data nodes, the name node hasn't been received the heartbeats for some time period, then it will mark this data node as dead and do some other operations to fix this problem. And every 10th heartbeat, there will be a block report. So the block report is like this. So this data node will tell the name node, so what blocks I have. And okay, so the name node will keep track of this information in the metadata part for each file. And name node also builds will build the data metadata from the block reports. So you can see, okay, if some data node is done, it's okay, it doesn't matter. But if the name node is done, which means that HDFS cannot be used. And so we need to check this problem manually. And HDFS cannot solve this problem by itself. Inside name node, there are some components. One is called the edit log as a site, so it's used to record the file operations transactions, such as when the file is created, when it is updated, and so it's called. This is about log. There's another component called fs image. It is a snapshot of the file system when name node started. A master copy of the metadata for the file system will be created. So it's like this. So this is a name node, and it will read at startup and merge with edit logs. So the when a name node started, it will read the two components. First is the fs image, which is a snapshot of the file system, and then also it needs to read edit logs because it records all the file operations. So this fs image and edit logs will be merged together to make the name node ready. And so you can see that only in the restart of a name node, so the edit logs will be applied to the fs image to get the latest snapshot of the file system. And if your HDFS has been run for a long time, and edit log will be very large, right? And which also means that you need to use a long time to start the name node because merging the edit logs with fs image will cost many time. And it is okay because normally the name node will not be restarted. This is very rare. It's not common in real clusters. But anyway, it still may happen sometimes. And the problem is that, well, the edit log becomes very large, right? So it is very challenging to manage such a big log file. And also the restart will take a very long time because there are many changes to be merged into the fs image. And in the case of crash, so we also may lose the huge amount of formatted data because fs image is very old. And that's why secondary name node is created. So remember, secondary name node is not a copy of the current name node. So it is utilized to help to overcome the above issue by taking over the responsibility of merging edit logs with fs image from name node. So for the secondary name node, it also has a fs image. So it gets edit logs from the name node periodically and apply it to its own fs image. And once it has new fs image, it will copy this new fs image to the name node and also update the edit log in the name node. And so as a result, so you can see that the fs image will be kept updating, right? So it can always receive the most recent update, and edit log for the very old logs for the file operations can be discarded, so edit log will not be very huge. And in the next restart of HDFS, it will not take too much time because the merge is much easier compared to without using this secondary node. So that's what the secondary node is used for. And in our labs, so what we normally use, do is enter this directory, that's UMP9313 user. So this is our username. It is very similar to a file system in our local computer, right? So actually, about APIs is just similar to a traditional file system. And what we can do is we can create, we can remove, we can rename, we can move, we can delete, we can do everything in HDFS. But what you need to do is the comments are a little bit different. You need to use HDFS, DFS, and then use the comments such as put, make dir, and rm, these comments. And name node maintains the whole file system tree structure. And any meta information changes to the file system will be recorded by the name node in the edit log. And an application can specify the number of replications of the file needed. So this is called replication factor of the file. So by default in HDFS, the number is 3, which means each block will be replicated for 3 times. And so this one figure from the HDFS homepage, which explains the data replication. So this is a block replication. In the name node, it maintains the following information for each file, which is the file name, the number of replicates, and block IDs. So for example, for this file, and the number of replicates is 2, which means that for the block in this file, so each block will be replicated for 2 times, and this is 3, and this is for 3 times. For file read and file write in HFS, because of time, I don't want to go into the details, so you can follow the number to see how it happened. And the client, you can think about the MapReduce job as a client, and it will contact the name node to get the block locations, and then read the nodes from the data nodes, and then finally close the whole communication. Write is similar, so HFS client also contacts the name node first, and the name node will tell the client where to write data, and this process will be pipelined, so from one node to another node to another node, and this is about write. And a replication engine will it will do the replication for data blocks. Once some data node is done, for example here that is done, A and C, blocks A and C now has only 2 copies, right? So in order to solve this problem, then this replication engine will take charge of this and to create a new copy for A and C in another data node to replace the lost blocks. And rebalancing is used to guarantee the load balance for your jobs, because the workers are moved to the data, right? So guaranteeing the data storage balance is very important for the computation balance. And this almost most of the times it happens when the there's not some task doing in your cluster, so it will not affect the other jobs. And the idea is that it will never affect the MapReduce jobs to just happen in background. And there's also a command line tool for the rebalancing, which means that you can do this manually. You can ask the Hadoop HDFS to do rebalancing now by using this command. Okay. And as introduced, the HDFS assumes commodity hardwares. So the failure is not exception, it's just normal. And HDFS instance will consist of thousands of server machines, right? So almost at any time, there will be some failures. And as a result, how to guarantee the fault tolerance is very important in HDFS. The major problem is that if your name node is down, then your HDFS cannot be used. So the FS image and log, they are the central data structures of HDFS. And a corruption of these files will cause HDFS instance to be non-functional. But if one data node is down, it is okay. So HDFS can solve this problem on its own. So this is a summary about the unique features of HDFS. It provides guarantees failure or fault tolerance, and data by using data replication. And each data block will always be replicated for some times to guarantee the availability, and also provide scalability. The data transfers will happen directly with the data nodes. So your read and write capacity scales fairly well with the number of data nodes. If there are more data nodes, which means that we can read and write the data much faster. And also guarantee the space. If you need more disk space, you just need to add more data nodes in your cluster and then do the rebalance. And it also can reach the industry standard. The other distributed applications are built on top of HDFS, such as MapReduce and HBase, and also actually Spark also uses HDFS for storage purpose. It will read the file from HDFS into memory and then do the other jobs based on the data in memory. And remember that HDFS is designed to process large data sets, not for many small files. And the pattern is write once and read many times. And also not for random exercise. Most time it's for the sequential read and write. And also it's not for low latency access. It's aimed to provide high throughput, not to provide low latency. So that's about HDFS introduction. And if you are interested, you can also go to the HDFS homepage to read more details about HDFS design. These slides actually most of the part is from the HDFS design webpage, and there are more examples and figures. Okay, and next topic is about the NoSQL system. NoSQL system is not NoSQL. It's not only SQL. It does not mean that we do not use SQL. It means that it's not only SQL. We have some other more features to do the data management jobs. So what does RDBMS provide? It provides relational model with schemas. Right? We have tables to store data, and also provides powerful, flexible query language. The SQL language can be used to do queries, and also provides transactional semantics, ACID, and rich ecosystems and lots of tools support, such as MySQL, and this one is used in the database course in our school. And NoSQL, the name is not only SQL. It does not use SQL as a query language because there are many types of the system in the NoSQL ecosystem, and it is a class of non-relational data storage systems. There are many different types of the data model, and this term was introduced by Eric Evans several years ago, actually. It's not a replacement for the RDBMS, but it complements the RDBMS. And all NoSQL systems offers relax one or more of the ACID properties in order to guarantee the high availability and the distributed data storage. Okay, so this is about the CAP theorem, and I will introduce the theorem later. What is the key feature of the NoSQL includes, first is, remember, NoSQL is a class of non-relational data storage systems, okay? So it is not relational data, it does not use relational model. It's not based on the schemas, tables, and tables. And NoSQL systems don't require strict schema. And the data replicated to multiple nodes and can be partitioned as well. And it is horizontal scalable. So horizontal scalable means that you can use more nodes in your cluster to increase to improve the scalability, to provide a more powerful storage. And this is called horizontal scalable. Another way is like RDBMS. On a single powerful server, you use more disks and to provide better scalability. So that's two different ways. It is cheap and easy to implement. So normally these systems are open source and also based on commodity hardwares, not on expensive hardwares such as a very expensive server. And it assumes massive write performance, provides massive write performance, and has fast key value access. So why we need NoSQL? It's just because applications of NoSQL and the applications of RDBMS are very different. So normally it's for web applications which can use the NoSQL systems. And web applications, the needs in web applications are different because normally the low and predictable response time is required, and scalability and elasticity is also very important. You must use low-cost hardwares to do many jobs, and must guarantee the high availability. And the flexible schemas and semi-structured data are normally used instead of the strict schemas and structured data, as in RDBMS. And the last one is that normally the data is distributed, not in a centralized manner. The data is stored in multiple data centers. And web applications can do without transactions or strong consistency or integrity. And also, web applications do not need to use complex queries to do the data analytics. So that's why in most NoSQL systems, it can just remove one from the ACID guarantees to guarantee these features that are required for web applications. Many big companies are using NoSQL systems right now. So Google, actually GFS is first developed by Google, and then followed GFS. HDFS is designed. HBase is this project is designed following a big table, the Google's idea. And LinkedIn, they also use NoSQL system called WorldMod, and Facebook use Cassandra. And in Twitter, they use HBase and Cassandra as well. In Baidu, they call it Hypertable, so which is also which also follows Google's big table idea. And this one, and also HBase, we will learn later. They are based on column, both key value ideas and also column database ideas. And there are three major papers for the NoSQL systems. The first one is Google's big table. And also following this paper, and the HBase project is created. And Amazon proposed their Dynamo system. It's also a paper based on the key value data store. And the last one is the theory support for NoSQL systems, which is called a CAP theorem. So what is a CAP theorem? Suppose there are three properties of distributed system for sharing the data. C stands for consistency, and which means that all copies must have the same value at any time. It's called consistency. And A stands for availability, which means that your system will be available at any time. So the request of read or write will always succeed, will always be supported by our system at any time. It's availability. And partition tolerance means the system properties, consistency and or availability still hold even when the network failures prevent some machines from communicating with each other. Okay, so the partition tolerance, I'll try to explain this again, which means that when there's some network failure and in your cluster, your computers are not able to exchange the data between each other, and consistency and availability can still be guaranteed. So according to the definition, it seems that you cannot achieve all the three goals, right? So if you want to guarantee the partition tolerance, it's very difficult to guarantee the consistency, right? Because if you do some update on this node, but this update cannot be reflected in another node because of the network failure. And then if another request is sent to that node, and the two requests actually, they will read different values for the same data. So which means it is not consistency. For the same value, actually, for this piece of data, actually they have different values, right? And so that's the idea of the CAP theorem. It means that for any system sharing data, it is impossible to guarantee simultaneously all of the three properties. And you can have at most two of these three properties for any shared data system. You can only guarantee two from the three at most. A very large system will partition at some point, right? So because we are assuming the very large data set and assuming the very large system. So we always want to get the partitions. We want to guarantee the P part. So if we want to guarantee P, which means that we can only discard C or discard A, or keep C or keep A, to build your system, right? And traditional DBMS is different. It prefers C over A and P. So in traditional RDBMS, consistency is always the most important thing. It tries to guarantee that all the copies are the same. And in almost all the cases, well, you would choose A over C for the web applications because availability is more important. It will provide always provides users some data to guarantee the availability. And except in some specific applications, such as order processing and other applications that the consistency is more important. So what does consistency mean in this CAP theorem? We can use a circle to represent the three properties: availability, consistency, and partition tolerance. And now, consistency means that all clients always have the same view of the data. So this is a whole cluster, right? Your cluster, your system will receive requests from different clients, and the different clients will fetch the data, maybe fetch the same data from different locations. And for the one data, there may be several copies. And consistency means that the copies for this data must always be the same. And this can guarantee that all clients will have the same view of the same data. And once a writer has written or has updated this data, so all the readers will see that write. So, which means that if you write the data on this node, this write must be reflected to the other copies, and the read request cannot be received, cannot be processed before the write synchronization finished. So only the synchronization of this write operation is finished, then the subsequent read request can be processed. So that's our idea. And there are two kinds of consistency. One is called strong consistency, and actually it's what we learned in RDBMS. It's ACID, automaticity, consistency, isolation, and durability. And in strong consistency, it's just like this. So once you write some data, you update some data, and this write or update must be synchronized to the other copies after this write is happened. Okay, and all the other requests must wait for this operation to be finished, for this synchronization to be finished. And another one is called weak consistency, and it's called BASE. So basically available, soft state, eventual consistency. And according to the name, it means that eventually, well, the data will be consistent, but not consistent at all the time. And in ACID, so DBMS is expected to support the ACID transactions, and so this is what we learned before. In CAP, it's these three properties. And now in the weak consistency, it is different from what we have learned in our database course. So it cannot guarantee the strong consistency. So after one write is a request is received, okay, it will write, it will update this data on this node, but the synchronization will not happen just immediately after this write operation. And the system will deal with the synchronization at some time point later. So finally, the data, all the copies will be consistent, but it does not mean that in the strong consistency and your read request must wait for the synchronization to be finished. But in the weak consistency, your read request can still be received and processed to guarantee the availability. But at this time, it means that some clients, they get different values, right? So some problems may happen. Now let's look at the consistency model. This model determines the rules for visibility and apparent order of updates. So for example, row X is replicated on two nodes on M and N. And one client A writes row X to node N. So it updates this row in this node N. And some period of time T elapses. So client B reads row X from node M. This is a copy of X on node M. So does client B sees write from client A? And so the consistency is just a continuum with trade-offs. So for NoSQL system, the answer would be maybe, not guaranteed. In RDBMS, the answer will be yes. So the client B will always see the same, will see the update on node M. So that's in RDBMS because ACID is guaranteed. But in NoSQL system, and the weak consistency model is utilized. So it depends on the time. If the time is long enough, then the answer would be yes as well, because it's called eventual consistency. But just a few seconds or a few minutes, then the answer will just be maybe. It's not guaranteed. The data is synchronized across the two copies. And CAP, this theorem states strong consistency can't be achieved at the same time as availability and partition tolerance. And if you want to guarantee the availability, or you want to guarantee the consistency, which means that the availability cannot be guaranteed because the read request must be held, must wait for the synchronization. And so the availability cannot be achieved at the same time of the consistency. So that's a basic idea of the CAP theorem. And the eventual consistency, you can see the wiki page here. The idea is that when there's no updates occur for a long time period of time, and eventually all the updates will propagate through the system, and all the nodes will be consistent, and all the copies will have the same value. And for given accepted update and a given node, so eventually either the update reaches the node of the or the node is removed from the service, from the system. It's also known as a BASE as opposed to ACID. So it's a basically available soft state eventual consistency, BASE. That's a theory foundation of the NoSQL system. And the types of large systems based on CAP, they cannot guarantee ACID. And they are based on BASE, so they're basically available. The system seems to work all the time, and soft state does not have to be consistent all the time. So as shown in the previous example. And you update this row X on node N, but if another read request for the same row in node M, and it's not guaranteed that the update can be reflected in node M. So the clients, if the read request is processed in both M and N, the two clients may see different values for the row X. But eventually, the data will be consistent at some later time. And all the big data NoSQL systems are based on CAP and BASE, not based on ACID. ACID is used only in RDBMS. Okay. Okay, so let's have a short break first, and then we come back. prefix 错了，因为如果 S 有提示吧，那你这个用的是一个但那我只是说我这个用的只是说我做算了，比如说我相当于是把我的 prefix 变长了，对，但是无所谓，我不说错。如果 S 不准，那 R 的话就是那前的话那 OK 那没错，对吧？是这个意思，就是让你稍微小点儿。
OK。还有就是说，就是这里讲的，如果它 prefix to 的话，那这个 week2 pair，
depends on 他们的那个 frequency， 前提是这个已经按 frequency
对的，按 frequency 但是就是这样的话就会出现一个 local。
对。
但是如果我们就
你可以这两个一起，你可以想办法去这些
那我就说，就如果是我们就以那个质量，如果它 P 然后这样的话，它可能就是每个 index 可能只有一个是 match
什么
就是 instead 就是 A B 然后 A B 这样的话，
那它的 key 是什么
？key 就是 A。这样的话，
那这个 key 太多，这个 key 就很难被 match 出来。这个就是说 OK，我包含这个 A 的 record 都会被放在一个那么对，然后他们都有可能是 possible 的 pair， 然后就算一下。对。但是如果你把这个 A B 当一个 key 的话，那就会出现这样一个问题。另外一个比如说是叫做 A C 的，对吧？就是 A C 和 A B 这两个分别是咱们前两个，但是他们并不是什么 key， 他们放在一起，但它名字是。
那就是说，就是它跟 A B 和 A C 好，但有一个肯定是不一样的，有一个如果是有一个 prefix 不一样的，肯定是。
我明白意思我可能要举个例子，我要举个例子可能怎么说呢？就是说你这样做可能会 miss 掉 result， 就是就会 miss 掉 result。你可以试一下，你如果只用前面上那个叫 prefix 上面去的话，肯定会 miss 掉 result。因为你想你的那个 mapper 是根据你如果通过什么手动的 key， 对，就是通过 key 来手动的，对吧？对。你比如说你这是
就我现在说的，
那你这个 prefix 并不是这个 prefix， 明白我的意思吗？因为在这儿的话，你说我这是长的 prefix， 算是长的，
是会 miss 掉的，
这是一个原因。但我现在还没有想明白怎么跟你说清楚这个事情。但这样做的话，因为会有还是有办法去重，比如说在重子上面算。
我觉得就是如果这样的话，所以可能是省下很多钱。
对你肯定时间快，你到你你可以试一下。OK， 再试一下，反正也不花多少时间。
所以他这个方法就是，只要 at least one code， 就肯定就确保是，因为他们有可能在。
对，
所以就肯定不会遇到。
对，肯定不会遇到。
I'm having trouble understanding how to get the
prefix.
Okay, yeah.
So if you understand this line, if there any problem on this line, on this equation.
Okay.
So do you have any question on this equation? On this equation? Any question on this part?
Not really, but what do I use though?
So you can see L is used in this equation to compute for prefix, right?
Yeah.
Then you need to use this number of prefix to decide how many keyword pairs you need to emit for each record, right? So that's the whole procedure. Okay. So I guess your question is how to compute this prefix, right?
How to get the L?
How to get this L?
Yeah.
Right? I guess that's a major question.
Yeah.
Yeah. Okay. So let's look at this question. This equation again. Okay. So it's about R and S, right?
Yeah.
So now the problem here is that I do not know what is S because you are only given R.
Yeah.
Right. So
does that mean I have to compare every record?
Yeah, but no, but check this again. So max R S.
Yeah.
So you can just use R in this equation to compute L. The reason is if S is longer, it's shorter than the R, so well this value is just R times tau, right? And there is no problem. And if S is longer than the R, so the real value is max is S the length of s times tau, right? But now you use the length of r times tau, which means you use a smaller L, but your prefix is longer.
Yeah.
But it's okay. Your prefix is longer, but you cannot miss any results. You just emit more pairs.
So basically, it's just t,
So
t times
what I mean here is that just use
t times the size of r.
yeah, that's it.
Okay. So, well,
这是第二步吗？就第二步。
okay. Then it's
So now giving you one record.
sealed. It's sealing.
Yeah,
Sealing.
Yeah,
Okay.
yeah.
So basically, you just calculate that equation,
That's correct.
and then you'll get the.
Yeah, that's why during the lecture I asked you need to think about how to compute the length L by yourself.
Yeah, I was
Just
thinking
now.
about that, but I didn't know if I had to go through
Okay.
the rest of the
Okay.
records. Okay, thanks.
我说可以说，
Okay.
就是他，哎，他这个第一步就是说我刚进来的时候，我这一整个如果是个大文件，它就分成这3个是吧？然后我把每一块里面的 count 一下。
哦，对，这个是这样的，他那个 paper 里面先做了一次排序，他这个第一个 phase 是做那个 frequency 的排序，然后我们今天的数据集给你的数据集是已经做好排序的，当然了，你自己做的话还是需要做一下排序，你可以之后做这一步也可以。这个第一步是做那个 frequency 排序，因为后面算 prefix 的时候需要你把每个 record 是按 frequency 排好的，从 low frequency 到高 frequency 都排好序之后，然后再去按 prefix 去取出来的东西，取出来的。
哦，那就
我们代码里还用写这个排序的过程吗？
需要的，因为测试数据集不见得是已经排好序的呀。否则的话，这个问题太简单了我给你们数据暂时是已经就是没排序，都已经排好序了的。就是这样的话，你们暂时当前的任务会简单一些嘛，不会考虑排序。但之后的话，还是要考虑一下排序的问题
啥意思？那他这个到底是按啥排的？就是按我输进来，他这个 ID 上面分的这一串东西，然后我统计一下它有多少。
这是原始数据集，然后你说这第一步在做什么，是吧？
对啊，这个。
他就在统计每个东西有多少个呀？
这个 C 为什么是2呢？
对啊，是因为它这一块
是因为第10个 record 里头有2个 C。
对啊。
咱们不是说 set 吗？就是 Java 的那个 distance 不是 set 吗？它不是把它放到 set 里头，那怎么会有2个？就是一行里它不是给它放到 set，这不应该有重复。
我们这个数据集我想有没有重复啊？我们数据集好像也没有重复的。我们的数据里应该是没有重复的，它这里面可能是有些重复的。
那我们要是就是说得实现不得实现是有重复的，还是因为你算 Java 的那个的时候，不是2个 set
如果
之间
是 set 的话是没有重复的，这个就是一个那个，就每一行一个 record 都是一个 set。
我们要不要假设就是都是一样，就 emit 都就是给它放到一个 set 里头，还是说我们要去统计每一行里头每个词的词频是多少，还是说不用统计，就是每个词都是一样？这个是根据
这个其实并不影响你们做的结果。
那这个排序有可能影响，因为你这个词如果说一个里头
我是说我们的数据集里是没有重复的，但是你这样做的话并不影响结果，对吧？对吧？我得去检查数据集，好像应该是没有重复的，我们的里面应该是没有重复的，但我不太清楚他为什么他这边是有。我不太清楚为什么他是这样。
那我们第一步就是一定要先把这 frequency set 完了之后，才能进行第二步那个 prefix 嘛。
对。
然后我想知道，如果我们用 Scala 写的话，那它还是格式是那个 key value 是这样吗？
你可以还是把它用一个 pair RDB 来做嘛 ，pair RDB 的话就是 key value。对吧？
就不用像之前在写一个 map 什么 reduce 那个东西都不用写。
跟 map reduce 没有关系，你现在是在 Spark 里面来做了，这就不是 map reduce 的 model。
那它这个就是说我这样子的话，就直接让它的这个当前读进来，它这一行这么长的话，按 frequency 排完了之后，那我把后缀这个东西乘以我要的那个比率，然后这个是它前面的吗？
对，前面这些 prefix 是你要的东西。你还是没有说什么意思是吧？
那为什么他们自动会把这个它是第一步之后就把它就分成这个样子了吗？
没有分成这个样子，就你的数据是什么样子还是什么样子的，只是说你可能需要看一下那个 paper， 就是你第一步已经做好了一个排序了嘛，对吧？做好排序之后，然后在这里面的 record 的时候，你这儿有一个 token 的一个列表，这个 token 列表就是你的排好序的这个东西，然后在每个 record 的时候，
你需要去通过这个 token 列表去把你的 top k 拿出来。比如说像这个第11个，第11个为什么只有 e 和 d 算了 ，c 没算？其实你要它就是因为 e 和 d 是那个更低频的嘛 ，c 不是更低频的。它并不是说你像这里边的话，它并没有把你的数据再重新排序，它没有去 reorder 你的数据集，它是根据这个 token 的 table 去把那个前边最低频的那几个 element 拿出来的，是这样子的过程。
这可以啊。正常应该是给它排下去，然后去选
你排序的问题是在于，你需要在整个数据集上都再重新再更新你数据集的话，这个比较慢，效率比较快，效率比较慢。
对，它这样肯定快啊，就是它挑出来是吧？前几个挑出来的。
它就是通过你的这个 token table 去把你这个 record 里面挑出来，其实也相当于是一个排序的一个过程嘛，只不过是它并没有去做实际的排序，它是通过这个 token table 已经有这个顺序嘛，然后通过这个 token table 把这边前面这个最低频的这几个东西在这一行里边把它拿出来就可以了。
为啥前面是啥都不他等一下，我先
你先问。
我等一下，就是说我先进来之后，如果我用进来，我是先把它后面跟的这个我 ID 后面跟的这个第一次的先排序。
你要排也可以，你要排序也没问题。
为啥排完之后它前面这个就是低频？
不是，你低频词已经在这算出来了。这个 token 不是有一个列表吗？这个 token 列表的话，这个 G 这个东西就是你的那个排好序的一个 table， 这是在第一步得出来的。
那这个东西，就这个东西，
看到了吗？它已经排好序了，在这个 T 里面。
那它这个是按一个一个排，它这 A 是它这个等个 list 对吧？
不是，
它这 A B 是等个 list。
A B C 这是一个，这是第一个 record， 第一个 record 里面有三个 element A B C， 这是第一行，对啊，
那我排是把它每一个 list 的每一个东西都拿出来排吗？
不，你现在的任务是什么？你现在任务是从，比如说 A B C 好了，假如说我的 prefix 是2，对吧？我需要从这3个 A B C item 里面选出2个出来作为 prefix， 来去 emit 你的 keyword pair， 对吧？那现在哪2个是最低频的？那你就通过这个 table 去找嘛，找出 A B C 哪2个最低频的出来，就是这个意思，还是那个意思。
行，我给你讲了。
Okay, so let's continue. It's about the previous is about consistency. Now let's look at availability. So availability in the CAP theorem here it means that the system is available during software and hardware upgrades and node failures. So the read and write requests can always be processed during the software and hardware upgrades and node failures. So that's called availability. So traditionally, the so we aim to reach this standard, the 5 nines availability, which means that about 99.99% percentage of the requests can be processed successfully. But the problem is that for large node system, and at almost any point in time, there is a good chance that the node is either down or there is a network disruption among the nodes, right? So what we want is a system that is resilient in the face of network disruption or even disk failures. So the availability is kind of dealing with the fault tolerance. When there are some faults happens in the system, and we are still able to process read and write requests. And the partition tolerance is about also about the network failure, and it means that the system can continue to operate in the presence of network partitions. So if there is some network failure and which prevents your computers to communicate with each other, and your system can still be available and can be used by the clients. And the theorem is that you can have at most 2 properties for any shared data system. And so based on this theorem and NoSQL systems, different types of NoSQL systems are developed. Either they prefer A or they prefer C, and they all guarantee P because it's for large systems. So the data is always distributed. So the partition tolerance is always guaranteed, and then only A and C left for you to choose which one you prefer based on different applications. For the NoSQL systems, so generally we can categorize them into 4 groups. The first is called key value stores. It just utilizes simple key and value lookups and giving you a key, and you can check the values in the table using some hashing techniques. And column stores is like this. So each key is associated with many attributes with columns. And NoSQL column stores are actually hybrid row and column stores. So not just column stores, but both row and column stores are used in the NoSQL column stores. And we will use HBase to see how the column stores are like. And the third type is called document stores, and store semi-structured documents such as JSON object or MongoDB. In MongoDB is also like this. Some semi-structured documents is used for the storage. And last one is called graph database. One of the most commonly used and popular system is called Neo4j. And it's not exactly a NoSQL system because it can't satisfy the requirements for high availability and scalability very well, but it provides APIs to manage the graph data. For the key value NoSQL system, it focuses on the scaling to huge amounts of data and designed to handle massive loads. And all these systems, most of them are based on Amazon's Dynamo paper. So the Dynamo system is our first key value column NoSQL system. And data model is a global collection of the key value pairs. And in DynamoDB, so the items having one or more attributes is organized like this: the name and the value, name as key, and this is the value. And the attribute can be single valued or multiple valued like that. The items are combined into a table. So the basic API is just like a hash table. You can get key, put key value, and delete key, execute the key operation based on some parameters. And the good part is that it's very fast for the data random access because it's based on key value model, right? So giving you the key, it's very easy to find the corresponding value by using the hashing technique. And also very scalable. And the data model is very simple. And also based on eventual consistency, can deal with fault tolerance. But the problem is that it cannot model the complex data structures such as objects or graphs, and they are hard to be modeled as key value pairs. So Dynamo is the first system proposed, developed by Amazon. And there are also some other, Redis is also one of the popular used system as a key value NoSQL system. And document-based can be used to model more complex objects compared to the key value NoSQL system. And the data model is a collection of documents such as JSON and XML or some other semi-structured formats. And in MongoDB, for example, one document could be like this. So this is a key, and it's a value for this key, for this attribute. And you can put them together as an object in this database. And MongoDB is the most widely used NoSQL system in this group. And the column-based, which is what we will learn in the next few slides. So it's based on Google's Big Table paper. It is like column-oriented relational database. So in column-oriented relational database, so they store the data in column order, not in the row order. But with a twist, so both the row and column are utilized in such systems. And the tables are similar to the RDBMS, but they can handle the semi-structured data, not the structured data. And the schemas are also more flexible, not strict schemas. And data model is like the collection of column families. And the column family is, in this format, the key value, where the value is a set of related columns. So a column family is just kind of a set of columns. And it's indexed by the row key, column key, and timestamp. So this is a data model. In one row, we use a row key to identify this row. And in this row, there are several column families. And in each column family, we can have several columns. So it's a big picture of this column-based NoSQL systems. And one column family can have variable numbers of columns. So that's where the schemas can be flexible in the column-based NoSQL system. And the cells within a column family are sorted physically. So in HBase, we can see how it is like. It is very sparse, and most cells have null values. So we don't need to store these null values cells. And compare RDBMS and the column-based NoSQL system. Well, the query on multi-tables in RDBMS must fetch data from several places on disk and glue them together. And on column-based NoSQL systems, they only fetch the column families of those columns that are required by a query. So remember that in your query, select from where. Actually, most of the time, you just select several columns, right? Not the whole row is useful for you. Only several columns are useful. So based on this, the column-based NoSQL system, they are able to just fetch the corresponding column families, not fetch all the rows, the entire row for the query processing. And Bigtable, HBase, and Hypertable, Cassandra are all in this group of NoSQL system. The last one is called graph-based and focus on modeling the structure of data. It can scale to the complexity of data. So this type of NoSQL system, normally it is utilized to deal with complexity of the data when the data can be modeled as graphs. And it's inspired by the graph theory. And the data model is just like a graph, a property graph actually. The nodes and edges can have properties, and the edges can also have labels. And the key value pairs are used on both nodes and edges. And interfaces, the query languages, well, they are quite different on different graph-based systems. And for example, Neo4j, FlogDB, InfoGrid, but I think Neo4j is most widely used and most well known. For NoSQL systems, okay, the advantage is that it guarantees massive scalability and high availability, has lower costs because it's built upon commodity hardwares compared to RDBMS, it's built on expensive servers. And usually it has predictable elasticity, and the schema is much more flexible. You don't need to define the strict schema before you store your data. So you can do some update for the schema. And the data is not structured. It's sparse, and normally it's semi-structured. And the disadvantages are that they don't fully support the regional features. For example, there's no join, no group by, order by operations, well, except within partitions. The major reason is that because data is partitioned to several parts, so if you do join, group by, order by, then these operations will have very, very high costs, communication costs. And there's no referential integrity constraints across partitions, also because the data is partitioned to several parts. And there's no declarative query language for you to use. So you need to do more programming jobs rather than just write SQL statements to do the queries. And the eventual consistency is not intuitive to the program for the client applications, well, it is much more complicated to deal with eventual consistency to guarantee the correctness of your algorithm. And it is not easy to integrate it with other applications that support SQL. Also, the theory foundation is CAP theorem, it's not SID. So there's fewer guarantees. And so it's up to your application. If your strong consistency is very important, then NoSQL system is not a good choice. It's not an option for you to use. You still need to use RDBMS systems to do your job. Okay, so that's a conclusion. And NoSQL database cover only a part of data-intensive cloud applications. Mainly it's web applications. So remember that NoSQL is not only secure. It's a complement of the secure systems, not a replacement for the secure system. So the secure system can still be used in many applications, especially when SID must be guaranteed. But in no secure system, it can be used for something like web applications where the consistency is not that important. So availability is more important. And you just need to remember this part for the NoSQL systems in our course right now. And so hopefully you can use this as a start. In the future, in your career, you need to use some NoSQL systems. Then you can start from here to get more documents, to read the relevant requirements of different systems, and make a good decision for which system you can use for application. Okay, and the third part is about HBase. So HBase is one column-based NoSQL system, and the idea is from Google's Big Table paper, and so we can use this to see what NoSQL system is like and what NoSQL system can be used for. Okay, so what is a HBase? HBase is an open source, distributed, column-oriented database built upon top of HDFS and following the idea of Big Table, Google's Big Table paper. So it is distributed. It uses HDFS for storage, and the row and both row and column store are used in this system. It is column-oriented, so the nulls are free. There are many values in the system is null, and it's multi-dimensional. So there are different versions, which means that the time is also recorded in the system, and it is untyped. So in HBase, it only stores byte arrays, not the actual type, integer, float, or string text, not these types of typed data, but only use a byte array to store everything. And HBase is part of the Hadoop project. It is a Hadoop application to use when you require real-time read and write random access to very large data sets. So remember that for low latency problems, and use HBase, but if you want to use, if your application requires high throughput, you can use HDFS. It aims to support the low latency random access tasks. What is the features of HBase can be summarized at this line. It is sparse. So first, in this, you can assume it is like a big table in HBase data storage. And in this big table, and it's very sparse. Many cells in this table is actually that they have null values, and it is distributed. So the whole table are stored in different computers, but it's based on columns, not based on rows. The split is based on columns, not based on rows, and it's persistent, multi-dimensional sorted map. Okay, so let's look at each attribute of HBase in more detail. So sparse data is supported with no waste of costly storage space. So in RDBMS, if in your table there are many null values, you still need to use some space to store this null value. Okay, but in HBase, you don't need to waste any space for null values. So that's the difference. And HBase can handle the fact that we don't yet know what the information is. So it means that the schema of your application can be very flexible. So although at this stage I don't know what information will be in the future, but I can use a column family to wrap this information. And in the future, if some new information is received, so I can create a new column for this unknown information. And HBase as a schemaless data store, it's a schemaless data store. I think it's not very appropriate. So it just has very flexible schema. So you can add to, subtract from, or modify the schema as you go along. So because it's not, the schema is not fixed. And distributed and persistent. These two features means that the persistent simply means that the data you store in HBase will persist or remain after our program or session ends. So the persistent. And just as HBase is an open source implementation of Bigtable, HDFS is an open source implementation of JFS. So in Google, previously, it's Bigtable plus JFS plus MapReduce for many big data problems. And Hadoop, in Hadoop projects, is HDFS plus JFS plus Hadoop MapReduce. And HBase leverages HDFS to persist its data to disk storage. And in HDFS, because it uses HDFS, so HBase can offer reliability, availability, and seamless scalability and high performance. So multi-dimensional sorted map. So multi-dimensional means that the data versions are also recorded. So for the same piece of data, and you can do some update, right? And you can define how many versions you want to keep in your system. So which means the updated value will not be discarded, but it will be kept there to remind you that previously the value is like this. So it's a previous version. And you can specify how many versions you want to use in the system. That's multi-dimensional. And sorted means that the keys are sorted in HBase, both the row keys and some other keys in HBase. And map is an abstract collection of the key value pairs, where the key is a unique. And the key here is it is a row key, and the value is for all the other parts in the whole row. So this remember the features: sparse, distributed, persistent, multidimensional, sorted, map. That's a data model for HBase. In the whole Hadoop ecosystem, and HBase is in this position. So upon HDFS, it's a Yawn. Yawn is a cluster management manager, and then it provides a resource allocation for HBase. So the storage is based on HDFS. The HBase files are internally stored in HDFS. Comparing HBase and HDFS, and both are distributed systems that scale to hundreds of thousands of nodes. And the difference is that HDFS is a kind of file system, and it's good for batch processing and scans over big files. So it also provides some APIs for you to use to manage the files, but you need to do a lot of programming tasks. And it's not good for record lookup. You cannot do random access. You can only do the batch processing, the sequential read or write. And also not good for incremental addition of small batches, and also not good for updates. All these because random access is not well supported in HDFS. And HBase is kind of data management system. So HDFS is not a data management system, it's a file management system. Okay, so think about difference. So the basic operating unit is files. Here, HBase is a data management system. It's designed to address these points in HDFS. It can provide fast record lookup because it is a map, right? So you can use a key to do the lookup to get the values. And it supports for record level insertion. So you can do some random access to get the corresponding cell in the whole table, and the support for updates as well. And HBase updates are done by creating new versions of values. So the old ones will not be replaced, but still be kept in the system. So a new version will be created in the system. And this is a table which better explains the difference between the two. So in HDFS, And the write is mainly just append. You can only append the new contents to a file. In HBase, you can do the random write and bulk incremental write. And for the read pattern, in HFS, it's just a full table scan and sequential scan. In HBase, you can do the random access and small range scan or table scan. So you can also read a range in the file. And for the performance of Hive, which is a SQL-like language on MapReduce, which will be introduced later. And in HFS, if it is upon HFS, then the performance is better than the performance on HBase. And the structured storage, in HFS, you can design your own structured storage, but normally we can just use sequence file to store the binary values. And in HBase is a sparse column family data model. And the data size supported in HDFS and HBase is a little bit different. So HDFS can support much larger data size. And what you need to remember is that, so if your application requires random access, random read, or random writes, you cannot use HDFS. You need to go to HBase for help, because only HBase can allow you to do the random write, random read. But HDFS can only support sequential read and write. Here is a summarization of the HBase characteristics. So the tables have one primary index, which is called the row key, and there's no join operators. And scans and queries can select a subset of available columns, perhaps by using a wildcard. And there are three types of lookups. The first lookup is based on the row key. So given you a row key, then you can get the contents of the whole row, and also you can specify the version, the timestamp, and a full table scan. So you can get all the data stored in the table. Or range scan, you can specify a start point and end point to read a region from the table. So the different types of lookups for getting the data from the data storage. And there is very limited atomicity and transaction support. And there's no access or manipulated using SQL language. So what you can do in HBase, you can use HBase shell to do some tasks. So in next week's lab, you can see how you can use HBase shell to create tables and to do some queries. And you can use the HBase APIs in Java or by using Thrift, by using some other languages. So normally we use Java to call HBase APIs to do some operations, such as creating tables, or updating some records, or delete some records, or do some lookup. Here we have three types of lookup, right? So we can use the keys to get the data we want to fetch. So this is a review of the ER model. In the ER model, we have entities and relationships, and then the entities can be connected by relationships, and the relationships has many types: one-to-one, one-to-many, many-to-one, many-to-many. And so this is a basic ER model. And in database, there are also some normalization techniques, right? So we have learned the first normal form, second normal form, BCNF, 3NF, 4NF. And these are used to restructure your schemas to get a good performance. But in NoSQL system, in HBase, we do not have these features. It's the data is not organized like this. The data can have two types: too big or not too big, right? But if the data is not too big, well, it's okay. We can just use a rich database to organize this data and to use some schema to represent the data. And the model is less likely to change as your business needs change, and you may want to just ask different questions over time. This is when the data is not very big. But if the data is too big, then much more challenges you need to deal with, because the original model does not acknowledge scale, and you need to split your data to different partitions and distribute your data to different partitions, right? And if the data is too big, and if you still use rich model, you need to add indexes to accelerate the performance. And also you need to write very complex and messy SQL to do queries. And also you need to think about how to denormalize your table to get better performance and think about how to cache some data. And the regional model is not suitable for dealing with big data. So NoSQL and HBase can help in such cases. And it is because HBase uses a different data model instead of the ER model in the RDBMS. What it uses, so let's look at more details. I can still be think about HBase has a big table, a very large table, okay? And in this table, it has multiple sorted rows, and the rows are sorted based on the keys. And each row is an atomic key value container with one row key, only one row key. And the rows are sorted alphabetically by the row key as they are stored. And the column in HBase, okay, here is a little bit confused actually about the name. So a column in HBase consists of a column family and a column qualifier. So in fact, the columns, they are contained in some, each column is contained in some column families. A column family is, one column family is a set of columns used to represent a set of similar attributes. And then within the column family, there's one column qualifier to identify this column within this column family. And the table schema only defines the column families. So this part is like RDBMS. In RDBMS, you need to give the schema for your table, right? And in HBase, you also need to define a schema. But this schema is not in the level of columns, it's in the level of column families. You need to give the name of the column families. For example, you have 3 column families, then you must give the names for 3 column families. But how many columns you can have is totally flexible. Within each column family, you can dynamically create new columns or delete some columns or update the column names. It's up to the data because maybe at this stage some information is not known, but in the future you get some new data, you need to do some updates for your schema. And now in HBase you can do this. But in RDBMS, the schema is strictly defined. You cannot update your defined schema. So that's different. And the column families, they physically collocate a set of columns and their values. And each column is a key in the key value container inside the row. And the value is a time version value in the key value container. And each column consists of any number of versions. The number of versions is defined by the users, how many versions we want to keep. And each column family has a set of storage properties, such as whether its values should be cached in memory or not. And columns within a family are sorted and stored together. So it's kind of, compared to RDBMS, what you have is a table, right? So in HBase data model, it's like it groups some of the columns in RDBMS as column families, But difference is that in RDBMS, once your schema is already created or defined, then you cannot change the schema. But in HBase, you can't change the defined column families, but within the column family, you can do arbitrarily to the columns. So that's why the schema is flexible in HBase. And each column is identified by the column family and column family name and the column qualifier. And given a column family content, so a column qualifier must be this one example, content HTML. So content could be the column family name, so which is the content of a web page, and HTML is one qualifier for column, so which means that this column is used to store the HTML content of this web page. And you can also have another column in this content column family, such as content PDF, so which is used to store the PDF files contained in this web page. And column families are fixed at table creation, but column qualifiers are mutable and may differ greatly between the different rows. For different rows, you can have totally different columns. And timestamp is used to keep track of the versions, and it's a long milliseconds. It's written alongside each value and is identifier for a given version of a value. You can use this timestamp to do the query to fetch the data to get which version you want to use. So by default, the timestamp will represent the time on the region server when the data was written. But you can also specify a different timestamp value when you put data into the cell, such as you can use 1, 2, 3 instead of this long milliseconds to add this timestamp. It's based on your application. And finally, the smallest unit you can operate in HBase is called a cell. This cell is a combination of row, column family, column qualifier, and timestamp. Finally, it is a value for this cell. And in summary, what you can do in HBase, in order to get value, you need to give the following information. First is the row key, so image row, the row key, and then the column family name. Which column family? In the column family name, you also need to give a column qualifier for the corresponding column, and then it's the version, which is a timestamp. So by giving this information, then you are able to know the value in this cell. So it's the smallest unit you can operate in HBase. So now look at one example in HBase. Assume that we are using this HBase using this table to organize web pages data. And this is a row key, which is a URL of a web page. So this is a row key. The column families are contents, anchor. There are two column families. And in this column family, we can use different qualifiers to represent different columns within contents. So remember, we can have HTML, or we can have PDF. And for each column, we can have different timestamp. The timestamp is used to represent when this piece of data is created. And finally, we have a value part to represent what data is like in the HBase. Physically, you can think HBase as like this. The row key is a byte array. It serves as a primary key for the whole table. And it's also indexed for fast lookup. So for example, here is a URL, which uniquely identify one row. And in this example, one row corresponds to one web page. And column family has a name, and actually they are used to group some attributes. And it contains one or more related columns. Each column is used to represent some attribute of this web page. And this is a name for this column family contents. And this is another column family anchor. And column qualifier belongs to one column family. It's included inside the row. For example, we can have contents HTML. So this is one column, or content PDF, this is another column. And in this anchor column family, we can see that anchor apache.com is one column, and this is another column, and my.look.ca is another column. So different column qualifiers. And this part is a value. And for each value, it also has information about timestamp, also called the version number. It's unique within each key. So by default, in the system's timestamp about when you created this value. And the type is long. But you can also specify what value you can use, such as I said, 1, 2, 3. And the value here, this is a value, and it also stored as a byte array. So physically, HBase table can be like this. Remember, it's a column-based, and the data are organized by the column families. And they can be indexed uniquely by the row keys. And within each column families, there are several columns identified by different column qualifiers. And the columns are very flexible. So on different rows, actually the columns can be very different. And the values also depend on the version, the time step when the value is inserted into the system. So it's about the whole table. So actually we can see that there are many entries which have null values if we really use a table to represent the information. And so as a result, HBase does not use a real table to represent the information. Remember that it is a sorted map. So actually it is a map instead of a table in physically on the disk. So let's look at this example to explain the HBase data model. We have a new HBase table, okay? And then we have two rows, enclosure 1, enclosure 2. And for the table, we have two column families. It's first column family is animal, and the second column family is repairs. And for the first column family, we have two columns. One is with column fair type, another one with column fair size. And in column family repairs, we have one column fair cost. So in storage, on disk, we do not store such a table as RDBMS does because it's too a waste of space because there are many null values in the table. So what we do is that we store every cell in the table. And it is stored fully qualified on disk, which means that each cell will be stored with a full row key, column family, column qualifier, and time step together with a value on disk. Okay, so for example, for this cell, in disk, what we need to do is that we need to represent this cell by this key value pair. The key includes the row key here, the time step, which is a version, the column the column family name, and the column qualifier within the column family. And the value is just the value of the cell. So on disk, as a site, we do not store a table as RDBMS does, but what we do is that we store these cells and in this format. And they will be partitioned according to the column families. They will be stored in different files based on the different column families. So that's data model and the physical storage for the data model. And this is another example to help you better understand how what HBase is like. So consider this table. We have two row keys cutting, and in the cutting row we have two column qualifiers, which is infer and rows, and in two different column qualifiers we have several columns as well. So first column family contains two columns, height and state, and rows has two columns as well, ASF and Hadoop. In the next row, we have some similar things, but we can see it's different, especially in the rows column families. In different rows, the column family names must be the same, but within the column family, the columns could be totally different. Here, only Hadoop, they just share this one, but they also have some different columns. So it's very, in this part is different from RDBMS. RDBMS, each row must have the same column structure, but in HBase it's totally different. It depends on the data, what columns you have for each column family. And so for the HBase data model, each row is atomic and gets flushed to disk periodically, but it doesn't have to be flushed into just a single file because there are different column families. So actually for each column family, there corresponds to one file. And it can be broken up into different files with different properties. And so one read can look at just as a subset. The column family divide columns into the physical files. So the columns within the same family, they are stored together. And the reason is because the HBase data model is designed because the table is sparse and there are many columns. So as a result, based on this design, there's no need to scan the whole row when accessing a few columns. Because many queries, actually, they only need to access some columns, not all the columns for the query, right? So in RDBMS, you still need to get the whole row because it's row-oriented data store. But in HBase, it's column-oriented data store. So you only need to access the relevant columns instead of all the columns of the whole row. And for each column of file, so the problem is, okay, so it's about storage of the column. So if you store each column to a file, then this will generate too many files. And instead, in HBase, they will have some strategies to decide how many columns will be stored in one file to guarantee the performance. And the row keys and column names and values, they can be arbitrary byte arrays. And table and column family names, they are printable characters, but they're also stored as byte arrays. And timestamp is a long integers, is the data type. So for HBase data model, given you a HBase schema, it consists of several tables, and each table consists of a set of column families, and the columns are not part of the schema. The column families are the part of the schema. So when you define a HBase schema, what you do is that you give the column families names for the table instead of the columns. You don't need to define the columns at this stage. And what you do about columns is you later, when you process the data, then you can create some new columns within this column family. So which means that the columns are totally dynamic. And the different cells can also have very different columns, just like as shown in this example. Rows and rows in two different rows, they have very different columns, although they have the same column families. And version number can be user supplied. We can define our own version number. And the table can be very sparse, so many cells are empty, right? So we don't need to store these empty cells. We only store the cells with values. And the keys are indexed as a primary key. So this is one conceptual view of the HBase table in the previous example for the web pages. So this is a row key and the timestamp and column family and column qualifiers and values. And this is another column family. So this is how HBase table is like. It's different from the RDBMS table. So physically, what we store is the cells. So for each cell with some values, and we can store them in the disk according to the column families they belong to. So in HBase, one H table is used to store column family. So each column family is stored in a separate file. So when you do some queries, if some column families are not useful, then you will never read those files from disk to memory. So only necessary I/O cost will be spent on processing some queries. And the keys and version numbers are replicated with each column family, and the empty cells will not be stored. So only the cells with some values will be stored. So for example, for the previous example, we only need to store the 5 cells for the very sparse table. And for this example, we need to store something like this. Okay, so again, it's still about the physical model. So column families, so each column family is stored in one separate file on disk. And so access one column family will not affect another column family, right? So we never waste the I/O on unnecessary column families when doing some tasks. And each table, which is used to store a column family, is partitioned into something called regions. So the first on disk, each column family is stored in one H table, is in one file, and then within each table for one column family, it is also partitioned into the regions. And so the regions are kind of similar to HDF blocks. So the size of the regions are fixed, and then each table is partitioned to several regions. So for example here, this is a file for the column family contents, and then the column family contents will be partitioned into several regions on the disk for storage and for management. Okay, so let's have another short break.
不好意思，我问个问题，那个这个到这一步的时候，这个里头就是给他们通过这个 key 就给它分到一起了，然后你相当于这个121在这里头做了一下，然后在这里又做了一下，
对
那不是应该做2遍？
对呀，所以说你要想办法不去做2遍，去把这个避掉。所以我说这个 paper 里的方法不是最好的方法，你一定要想办法去把这种操作避免掉。就是说它只算1次，不需要多算多次。
这个意思。 这个为什么 C 跟 E 放一起了？这个 C 跟 E 为什么放一起了？
哦，这就是那个它的 key partition 嘛，就是说是不同的那个 reducer 上，因为那个到底一个 reducer 能处理多少 key 是不一定的，就是说这是可能在3个 reducer 上，这个 B 可能是在这上面处理的，A 在这上面处理的，然后这里面 C 是在这样处理的。
它 group by key 这俩不是一个 key 啊，怎么？什么意思？没看懂。就是它俩 group by key 嘛，它俩不是一个 key， 那怎么还 group 到一起了？
那 group 到一起了？
这不 C 跟 E 吗？这不在一个 group 里吗？这 C 跟 E 吗？这 BB 这 AA 这个我理解。
我觉得它不应该是一个 group，
它意思是一个 partition 是吧？
我只能这么理解，它肯定不在一起，因为 C 和 E 不应该放在一起。你要比较的时候 ，C 和 E 应该是分开的，是对于一个 key C， 然后不是 group by key， 它是说，哎呀 group by key， 按理说的话，它应该是说把这些东西 group 到一起，根据像什么 key， 这确实是不是说你理解的那个就是 C 要一起处理。你像看这两个 C F D F， 就一个 F 是相同的，这跟 C 也不相关，跟 E 也不相关，它俩不应该在这儿处理，它俩应该是在 F 那边被处理才对。
这个都是0.5，就是都是那 threshold 写的，还是说算出来的？
那算出来的值，它这只是一个 example， 它只是一个 example， 它并不是实际的值。当然这里面的例子可能有些地方是有问题的，你不一定一定要 follow 它的例子，它就是看它的那个具体的过程是怎么做的。
我想不通为什么它会比原来那个快呢？因为原来本身人家就比一次就完事儿了，就是每2个比一次，就是算一。
不是，你现在的话是不用比这么多的，你之前你不用 prefix 的话，你要比很多个 pair。那你
prefix 是0.5的话，不是，就是那个 threshold 是0.5的话，相当于原来是长度是这么长，然后你现在相当于比它一半吧，对吧？
类似于这个概念。并不是 exactly 这样的。
其实还是在这基础上更新自己。
就是如果你不用这个 prefix 的话，你要算很多很多的 pair， 但问题是很多很多 pair 其实并不需要算。它的 prefix 就帮你过滤了一些不需要算的东西，所以就加错了。
但是你过滤的时候，是不是就是也是在比 prefix？
不是，就是 prefix 就第一步就先帮你滤掉了一些根本就不需要考虑的东西。你再想想那个 prefix 的原理就知道了。主要是那部分就是这个 paper 的主要贡献就在于它用那个 prefix 来加速了这个过程。但是这一步重复这块它并没有处理好，你们要想办法说怎么把这个重复的东西给去掉。
然后理解对不？就是先做一个 filter， 相当于就是过滤到一些非常不相似的，
对，
然后再做那个就是
相
pairwise 的，
对，没错，是这个流程，就是2步走的一个概念。
谢谢常老师。
Okay, so let's finish the last part of this lecture. I'm sorry that this lecture is a little bit boring, I know, and also not easy to follow, I guess, because it's not very interesting. But how to say, the problem is that I try to put everything together into one lecture. So as a result, I'm not able to provide more examples to you. So otherwise, these topics should be very useful and also should be interesting. And I hope that if you are interested, you can try to find some documents on the internet and do something on your own to see the usefulness of these projects. So HDFS is okay. We have already used HDFS for many projects. So in both MapReduce and Spark projects, we use HDFS. And for NoSQL systems, and a good example is to use MongoDB as an example, or use Neo4j to show you how to organize graph files, graph objects. But the problem is that we do not have enough time. So if you have time, you can try to do it by yourself, to try MongoDB and to try Neo4j, and to see what kind of applications they can be used. And for HBase, and so next week we will have a lab for HBase and Hive. But I think most of you will work on project 4. So, but anyway, so I will provide the documents to you. So it's up to you to if you are interested in these topics. Okay, so anyway, so I'll try to finish the last part about HBase and Hive. And HBase and Hive, these two projects are still very active. And So when I first introduced this course, big data course, I also introduced some other systems. But many of the systems at that time is popular, but now they're almost dead, and no one will use them. And there's no updates for those systems, so they are removed from the course, from the lectures. But HBase and Hive, they are still evolving, and many companies, they are still using HBase and Hive for their applications. So at least I know. I have some friends who work in some companies in China, and to dealing with big data, they still use Hive to do the data analytics, and they told me that Hive is actually very useful and easy to use for MapReduce jobs. And okay, so it's HBase. So what we have learned before is the HBase data model. So remember that, conceptually, you can think about HBase table still as a table, but very sparse table. But physically, we don't use the table representation on disk, but instead we will only store the cells with values. And so each column family corresponds to one separate file called htable, and each file will be partitioned into the regions for organization. And so that's a structure, the physical structure of HBase tables. And about HBase architecture, it's also like the master and slave, this architecture. The master server is called hmaster, and there's only one master server responsible for coordinating slaves. And for the hmaster is very similar to the name node in HDFS, right? Because they both follow the master-slave design model. And the region servers are called HRegion server. They are used to store the real data in HBase, are used to store the regions. And remember that what is a region? One region is a partition of a column family HTML file. So some cells, just a set of cells within one column family, sorted according to the keys. And the HBase client can connect with the master and the region server to get corresponding data. So what we have learned before about MapReduce is that the MapReduce will interact with HDFS directly. So MapReduce asks for data from HDFS, but actually MapReduce can also read data from HBase as well. And so MapReduce can be the HBase client. This is the whole architecture of HBase. So it's a HMaster, and HMaster is in charge of the coordinate region servers. And in each region server, there are some logs to store the operations. And so each region, just need to remember that the region is partition of the column families file. So that's a basic architecture of the HBase. In region server and in HBase, they also will have some, so HMaster and HRegion server, they also have some communications, just like in HDFS. And the client will connect with HMaster and HRegion server to get corresponding data. And HBase is built upon HDFS. So the HRegion server, the low-level H files, actually they are stored as data chunks in HDFS. There is something called Zookeeper. So the Zookeeper is used to do the coordination and the resource management and data synchronization in the cluster. And HBase depends on this Zookeeper manager, cluster manager. And by default, HBase already integrates the Zookeeper server. So when you download HBase and install HBase, so Zookeeper actually is already installed for you. And this is by default. So HMaster and the region servers will register themselves with Zookeeper. So the Zookeeper will keep the relevant information for the HMaster and the region server. and then clients can contact with the zookeeper to get the relevant information to fetch the corresponding data from the region servers. So that's the whole architecture of HBase. And in next week's lab, you can see how to install HBase on your computer and how to use them. So you need to have Java and Hadoop installed first. Then you download HBase. The current version is 2.0.0. It's released this year, several months earlier. And installation is very easy. You just download the package and compress it, and then you need to configure some environment variables in this file. Then that's all. That's just it. Oh, okay. You also need to remember to do some configurations for HBase to let the zookeeper to manage the cluster and also to tell where is the Java home for HBase. So then for this HBase site XML, also do some configuration like this. So the detailed instructions will be given in next week's lab. Okay, after doing all these configurations, we can start HBase using this shell script, and the shell will be launched by using HBase shell. So you need to start HBase first, and then you can enter the shell like this. So what you can do in this shell, you can create tables. Here, for example, we can create a table called test. And now after we create this table, we can list the table we can list the information of the table. So list, so we can see there's a table test that contains only one row. Now you can put data into the table. So we can put test, the row 1, data 1. So data here, that is the name of the column family. So the column family name is data. 1 is the column qualifier, which means the first column in this data column family. And the value 1 is just a value for this cell. So we do not give the version number. So by default, it is time step of inserting this data into the table. And this is the second row, this is the last row. So we can see for different rows, we have the same data family, but we have different column qualifiers. We have different columns for different rows. And then now we can scan the whole table. We can see the results. So we have 3 rows. In each row, we have 1 column family. And within each column family, we have different columns. So this is column 1, this is column 2, this is column 3. So remember, it's different rows, okay? So if you visualize this table, it should be like 1, 2, 3 on 3 rows, but not 1, 2, 3 here, like this. And timestamp is used to record the version of each cell, and these are the values. So you can see put is used to insert some new data into the table, and describe it to let you know what are the attributes of the created table. And you can also get a single row of data by using the row key. For example, get test row 1, and then you will get this row. This row contains 3 cells. They both have the row key as row 1. And you can also assign a defined table to a variable, use a variable for the operation. For example, T, you use T as a name for this as a variable to represent this table test. And then later you can use this variable to do the operations for the table. T.get, then you'll get the row with this key row 1. And you can also disable a table, then the table will be disabled. Then after the table is disabled, you can delete the table, and the table will be removed from the system. So before deleting a table, you always must disable the table first. Otherwise, you are not able to drop the table from the system, and you can exit. Just like SQL, you can also enter the HBase shell comments into a text file and execute this as a script. So everything will be, every comment will execute in HBase. And so finally, you can get a table test and then see some results of the get. Comparing HBase and RDBMS, so HBase has no real indexes, and the partitioning happens automatically. So it will partition the table for you automatically. You don't need to do this. And it scales linearly and automatically with new nodes, which means that for your cluster, if you want more storage, you want more disk space, you just need to add new cluster nodes into the cluster, and then the data, the rebalancing will happen automatically in HBase. It will automatically reorganize the data in the different cluster nodes, and it's built upon commodity hardwares and also deal with fault tolerance and suitable for batch processing, and also because it supports random access, so it's also suitable for low latency applications. And this table also better compares the HBase and RDBMS. So for data layout, so RDBMS is row-oriented, and HBase is column family-oriented. It's not column oriented, it's column family oriented. Because each file is used to store the one column family data. And the transactions for RDBMS is a multi-row SID, but in HBase it's only a single row. And there's no query language in HBase. You can only use APIs, get, put, scan to do the queries. So which means that you need to do some programs in order to query some data in the table. And there's no security support in HBase, and the index is only for the row key. But in RDBMS, you can do this on arbitrary columns. But the data size that can be supported by HBase is much, much larger than RDBMS. The scalability of HBase is much better. And read and write throughput is also much better in HBase. So when to use HBase, so if you need random write, random read, or both, when you need some random access in your application, so you need to use HBase, and otherwise you always stick to HDFS, because HDFS can support much larger data set. Or if you need to do many thousands of operations per second on multiple TP of data, you can also use HBase. And all your access patterns are well known and simple, you can use HBase. So in next week's lab, you can do some practice based on HBase. And hopefully this can help you to have a better understanding. Okay, so the last topic is Hive. It's also just an introduction because of time limit. But I have to say Hive is very useful, especially for very big data sets. And if you remember in Spark, when we learn Spark, we also learn a Spark SQL, right? So Spark SQL actually learned a lot from this Hive project. Both two projects, the objective is that many data analytics, these people, they have very rich experiences on SQL languages, but they are not able to do programming, to write programs, right? So for these people, and such projects will be very helpful because they provide a SQL-like interfaces. Well, Hive is built upon MapReduce, and Spark SQL is built upon Spark. But anyway, for the interfaces, if you know how to write SQL languages, then you can use MapReduce and Spark to do many data analytics jobs. So that's objectives of the two projects. And they also they helped a lot of people to do data analytic jobs. So what is a Hive? So it's a data warehouse system for Hadoop that facilitates easy data summarization. So now the data is summarized as tables. And it supports ad hoc queries. So you can use SQL-like languages to write some queries, select from where. And so that's the Hive's objective. And it is a mechanism to project structure onto this data and query the data use a SQL-like language. It's called HiveQL. And in Hive, there are also interactive console a shell, then you can, just like SQL-like systems, such as MySQL, then you can use a shell to do some tasks. And you can also execute scripts. And you can also use APIs provided to interact with some program. And so finally, this will be compiled to the MapReduce jobs. So in the lower level, so actually everything is still executed as MapReduce jobs. And it is an ability to use indexes and built-in user-defined functions. So you can also define your own functions to do some tasks within Hive. And for MapReduce, so remember that when you write MapReduce jobs, you need to write a lot of code, right? You need to use a MapReduce model. So you need to think about what should be in the mapper, what I can do in the reducer. And also it is not reusable. So for the two very similar tasks, you cannot reuse the code of another program. You still need to write a lot of codes or do some copy and paste. And for complex jobs, there are multiple stages of MapReduce functions, such as like in the second project, right? In the second project, you need to write many stage of MapReduce functions, and so very complicated. You need to control the flow of the MapReduce jobs manually. You need to specify what job should be done first, and then which job and which job, and so you need to give the flow of these jobs. And it's kind of like to ask a developer to write specified physical execution plan in the database. Okay, it's kind of you define the execution plan for a data analytic problem. So for the higher projects, the intuition is that to make the unstructured data looks like tables, regardless how it really lays out. So to use table view to facilitate the data management. And the SQL-based query can be directly against these tables, because now the data is already represented by tables, right? So you can use query-like languages, SQL-like languages to do the queries, rather than writing MapReduce jobs. And it generates specified execution plans for this query. So you don't need to specify the execution plan, but Hive will do this for you. Hive has a subset of SQL covering the most common statements, so such as creating tables and do some updates and select from where all these clauses are supported in Hive. And also provide agile data types, array, map, struct, JSON objects. And you can have your own defined functions and aggregates. It also supports regular expression. And all these will be compiled to MapReduce jobs. And also support JDBC. And you can create views and indexes based on the table view of the data as well. So this is about the word count, remember, so that's what it is look like when you write a word count MapReduce job, a lot of code. And so Spark is much easier, right? And using Hive is also much more easier. So this is about how you can use Hive to write a word count. Just several lines. First, you'll create a table doc. And in this table, there's only one column. This column is just a string of type string with name text. So the idea is that, okay, so after creating this table, then we read a file into this table. And the file will be split into words, and each word will be one row in this table. And then next, you do a group by for this table. You can get the count for each word. You get the frequency of the word in the documents, right? So that's the basic idea. So here is you create a table, and then you load data into load the file into the table, and then what you do is that you do select from clause and some other functions, and then do a group by. So finally, you can get a table contains both the word and the frequency. So later I'll explain what does these lines mean. Okay, so architecture of Hive is like this. So in Hive, the driver is a main component. It is compiler optimizer executor. It compiles the Hive statements and also do some optimization and executes these statements as MapReduce jobs. It's built upon Hadoop MapReduce. And upon the driver, well, there are several ways to write Hive jobs. There's a command line interface, and there's a shell, a console for you to use, a web interface, and you can also use JDBC or ODBC to interact with Hive. And Hive also provides some APIs for you to use. The meta store is used to, this component is used to store the system catalog and the metadata about the tables created in the system, and also contains columns, partitions, etc. It's stored in a relational database. After you download Hive, actually you can also see a Derby database, a relational database, a small relational database used within Hive to organize metadata. And the driver will manage the life cycle of a HiveQL statement as it moves through Hive. It will compile the query as to MapReduce jobs and do some optimization, also execute these jobs upon MapReduce. And this thrift server is used to support cross-language. You can use different languages to do the Hive jobs. And so, for example, you can use JDBC or ODBC to write Hive QL statements. And the other client components, such as CLI, web interface, JDBC, ODBC, allows you to use Hive. And how to install Hive is also very easy. You just need to download the package and compress it, and then do some configuration. So that's all. Then you can start Hive shell. So in all this, across all the systems we have used, so MapReduce is the most difficult one to configure. It's many configurations. And for the others, such as Spark, HBase, Hive, they are very easy to install and configure. And in the Hive system, well, now I think you should be very familiar because it's very similar to RDBMS. First, it supports many primitive types, such as integer and Boolean, float, double, decimal, string, character, variable character, timestamp, date. So this is very similar to RDBMS database system. And also support complex types, such as structs, maps, arrays. So for example, we can define a list. A list contains a map with string as a key and a struct as a value. In this struct, there are two components, P1 and P2, both integers. Okay. The Hive data model is like this, so it's still similar to RDBMS system. So name space functions is used to avoid naming conflicts for tables, views, partitions, columns, and so on. So you can define namespace first, and everything will be within this namespace. And the tables is homogeneous units of data which have the same schema. And you can think about tables just like a relational database, just a table, a schema. And each table has corresponding directory, HFS. This is about physical storage for a Hive table. And for example, if you have a page views table, and in this table, you have the following columns or attributes. You have timestamp, you have user ID, page URL, referral URL, and IP address. And for these attributes, so you can give different types for them. And now a table is created for you to use. So that's the parts that are similar to traditional RDBMS. These two concepts are new, are different. That's the parts that are different from RDBMS. First, called partitions. So each table can have one or more partition keys, which determines how the data is stored. So because Hive is also built upon a distributed computing environment, so the data they can be stored in different nodes. So the partition actually determines how the table can be partitioned to different parts. So for example, given the table page views, we can define two partitions, a data partition of type string and a country partition of a type string. So this can be used to partition the data according to two attributes, date and country. And partition columns are virtual columns. They are not real columns. They are not part of the schema, but they are used in the physical storage. So it is your own job to guarantee the relationship between partition name and the data content. And buckets is a data in each partition can be further partitioned, further divided into buckets based on the values of a hash function of some column of the table. So you can define the number of buckets for a partition, such as 16 or 32, and then based on some hash function, all the data within a partition will be divided into 16 or 32 buckets. So then now the data actually will be distributed to different small files, not small files, to different files, and then they can be stored to different nodes. So data model storage is like this. So for example, this is one table, okay? And the whole database, and each table in this database corresponds to one directory. So for each table, there's one directory. And for this table, you already have a schema for this table. There are several attributes, okay? And what you do in Hive is that you need to give the partitions for this table. How to partition the table according to some attributes. So in the previous example, we have the date and country. So it's based on the date of the data and the country of the data to do the partition. And so each partition also corresponds to one directory under the table directory. And each partition can be divided into buckets. So the buckets are the files used to store the real data. So now let's look at this now. Also, this is table 1, this is table 2. And on disk, table 1 has one directory, table 2 has one directory. And now the partition, date partition. So we have two partitions. One is in 11, another one is in 12, in November, and one is in December. And in the two partitions, so we define number of buckets at 3. So each one is divided into 3 buckets, and each one is stored as a file in on the disk. So that's a data model and a storage model in Hive. The next is about how to use Hive to do the data analytics jobs. So okay, here is again similar to what you have learned in your database course. Okay, here for example is the syntax of create table. Okay, it's a little bit complicated, but you just need to focus on some comment. Create table. Okay, create table, and then you give the table name, and give the column name and data type for the column and some comment to this column. And you can also give the comment for the whole table. And difference here is that you need to show partition. How to give defined partitions in the table is also important in Hive. It determines your physical storage of your Hive table. And cluster by is about the buckets. So how to define the number of buckets. So the cluster by some column name according to these columns, then the whole partition will be divided to the number of buckets to these buckets for storage. And the row format is about the format of your row in the table. And stored as file format is about the file format, such as binary, text, or some other format. And so there's detailed documentation can be found here. It tells you how to define a table and give you some example. And in Hive, there's something called ser. There is serializer and deserializer. This is a short name for ser is a short name for this. It describes how to load the data from disk, from the file, into a representation that make it looks like a table. And Hive uses this assert and file format to read and write table rows. And the flow is like this. From ATFS files, so first it input file format to get key value pairs. And from key value pairs, so the deserializer will deserialize the key value pairs to row object, and this row object will be put into the Hive tables. And the serializer, it means that you serialize your table to disk, to the bucket files, right? And for the row object, using the serializer, so serializer will serialize row object to key value pairs, and the key value pairs will be written to ATFS files by using the output file format. So that's the serialization and deserialization in Hive. You can load data from disk to a Hive table, and you can also write your Hive table to disk files. And for the row format, you can define how the different columns are delimited, such as the comma or some other characters. And also the different delimiters. So for example, let's look at an example. Okay, yeah, you can use Control A, Control B, Control C, new line. For different characters can be used as a delimiter. And there's a row format. The file format could be sequence file or text file. So sequence file means the binary file. And it's stored as a 0101 binary values. And text file is default, and it's stored as texts in disk, and also other file formats you can use. So for example, we can create table page view. So that's what we used before. This table page view has the following columns: view time with type integer, user ID with big int, page URL, which is string, refer URL string, and IP string. And this IP column has a comment, IP address of the user. So where the user has viewed this page. And this is a comment for this table. This is a page view table. And partitioned by two partitions, DT and country, date and country. Both are of type string. Clustered by user ID, sorted by view time into 32 buckets. So as a result, within each partition, and the records or the data will be clustered by the user ID to 32 buckets and sorted by the view time in the file. And the row format delimited is that okay, the field terminated by this control A, which means that each column is separated by this control A character. And collection item terminated by control B. So collection means that such as map or array or struct. These are the collection items delimiter. And the map keys terminated by control C. So in a map, remember that in a map there's key and value, right? So this is a separator for the key and value in a map object. A line is terminated by, so these are different rows for different rows. So you read one line, so this line will correspond to a row in your Hive table, stored as text file. So this means that when you write your table to disk, what you will do is like this. So first, your columns will be separated by this character, and then your rows will be separated by this character. And for the complex data structures, such as map, the key and values will be separated by this character, and other collection items will be separated by this character into a text file on disk. So that's how to create table. And next, you can use different commands to do various tasks, such as browsing tables and partitions, and do some update, alter table, partition columns, and drop table and partitions. I don't want to show more details because of time. So just remember, it's very similar to the SQL language. If you know SQL, you would be able to use Hive in a very short time period. And this is how to load data. You can load data from file, and the file can be in local file systems or in HDFS. And load the file according to the format as a table, as a half table in memory. So here is one example. So you load the data. Local means that your file is stored locally in a local file system. This is a path of the file into a table page view and to this partition in this year, month, and date, and country US. So now the corresponding file will be loaded into a table. And so this is about how to load a file in HDFS. There's no local command. So you load this from HDFS into the page view table. So remember that your input data format must be the same as the table format. So if the file format, the data format is not consistent with the table format, this loading process will fail. And here's about how we can update the table. You can insert rows into a table. The syntax is like insert into table, the table name, which partition, and the values about the corresponding values you want to update. And you can also use the query results to update the data. For example, you can insert override table user active. So this existing table, you want to insert some data into the table. Then you select the user, select everything from this user table where user.active is 1, if there's an active user. Now, from the query results, you insert these active users to this table. So it's similar to the RDBMS, right? And this update, how to update existing data. And this how to do the queries. And queries is also very similar to what you have learned about select, from, and where conditions. So group by, order by, cluster by is also group by and order by. They are also supported in Hive. So you can use group by and order by to do the queries. And limited number means how many records you want to view in the results. So the only difference here is that about the order by and sort by and cluster by. So these are different behaviors in Hive. So in RDBMS, it's not a problem because there's only one. It's a centralized computation, right? But now it's a distributed computation. So the difference between order by and sort by is that the former order by guarantees the total order in the output, but sort by, the latter, only guarantees the ordering of the rows within a reducer. Okay, and what is the total order? So this is called the total order. Okay, so in the order result files, the records are sorted, and sort by is the kind of a partial order, not the total order. So just within each partition, the order is guaranteed, but across different partitions, the orders are not guaranteed. And cluster by is a shortcut for both distributed by and sort by. And the Hive uses the columns in distributed by to distribute the rows among reducers. And all rows with the same distributed by columns will go to the same reducer for processing. And the distributed by does not guarantee clustering or sorting properties on distributed keys. So sort by will further sort the result. So it's a cluster by. So the difference is just the total order or partial order. And so for example, so we can select something from a table and where according to some condition. Okay, so it's very similar to what we have learned in the database course. So insert is insert with some comments, and group by and joins, they are all supported. So behind the scenes, and these statements actually are compiled to the syntax tree, and these are further compiled to one or more MapReduce jobs. And in Hive, you can also define your own functions and also some built-in operators. So such as max, min, count, some data functions and mathematical functions are also supported. And you can also define your own functions. So explode, this function that is used in word count example, right? So explode, it will return one row for each element from the array. So it explode array. So let's look at word count example again. We create a table, okay? And this table has only one row, one column. It's a text string. So next you